All right, so if you take a look, objective for today is to now move into, here's an equation that's in polar form, can you graph it? Okay, using your lab sheets to make a quick sketch. Okay, just using your lab sheets, not using your calculators anymore. So if you take a look, here's the first thing. We started talking about this yesterday. With circles, I would highly suggest you people on their phones right now pay attention. You've been working on this for 3 days. I'm now telling you what you should find. So just a quick heads up, I would put the phones away and focus here. When you get to circles, circles are pretty straightforward. We talked about this yesterday. There are 3 things that you need to know about circles. Where's the center of the circle? What's the radius, so you can use it to sketch in the circle, and the location. And we'll talk about those 3 things. Okay? These go pretty quickly. First 2 kind of go together. The center and the radius are both whatever the a value is divided by 2. It's half the a value. Okay? So in your equation, if a is 4, you know you've got a radius of 2. And you know that the center of the circle will be at 2 on one of the axes, which we'll talk about location in a second. Okay? You know the center of the circle would be at 2 as well. When I talk about location, here's what I'm referring to. And this really goes for a lot of these different ones in terms of not only circles, but the limacons as well. When I talk about location, the circle could be on like the positive x-axis, if you will, the 0 degrees. The circle could be on the 90 degrees, the positive y-axis. It could be on the 180 portion, or it could be down here on the 270. It could be in any one of those 4 spots. Same thing with limacons. When you get to cardioids and all those things, same idea. Here's how you tell where it is. 2 things. We talked about this a little bit yesterday. Sine, if you remember back to the unit circle again, those are the y-coordinates. That means any circle equation that has a sine in it is going to be on the y-axis. It's either going to be above on the 90 degree or down below on the 270. And how do you tell whether it's above or below? The number in front. If the a value is positive, it's on top. If the a value is negative, it's on the bottom. Okay? Same concept with the cosine ones. Cosine is x on the unit circle, which means the circles will be on the x-axis, either the 0 or 180. How do you tell? Same way. If a is positive, then you're on the positive side of the x-axis. Okay? You're on the 0 degree. If a is negative, you're on the 180 side, okay? The negative side of the x-axis. So sine is on the y-axis. If a is positive, it's above. If a is negative, it's below. Cosine is on the x-axis. If a is positive, it's to the right. If a is negative, it's to the left. Okay? Does that make some sense? And if you put those pieces together, you can pretty quickly graph a circle. Okay? Most of this is coming from A. The only thing that's not is whether it's sine or cosine. Okay? The location on which axis you're on. Otherwise, pretty much everything else is coming from A when you're dealing with circles. Okay? Any questions on that? Any questions that you have on circles? Okay, those are pretty quick. Those are probably the easiest of the 3. I would say those are probably by far the easiest of the 3. If you go to the next one then, the next page, the roses. I would actually say these are probably the hardest of the 3. It's just my opinion. Mainly because of the location of the petals. Okay? That would be why I say this is the hardest of the 3. But as you take a look, here again is the stuff that you need. You need to know what is the length of the petal so that when you're sketching it, you can actually have an accurate length. How many petals do we have? And again, where are the petals located? And that's the part we'll talk more about today. Length of the petal. Very simply, what's the length of the petal? What'd you find? A. The A value is your length of your petal. Okay? So that is A. Whatever value, and you can ignore the negative. If it's a negative A value, you can ignore the negative. It's the value, the number of A is the length. Okay? Number of petals. This kind of comes into 2 parts. Okay? And what it relates to, what you should have come up with, you should have figured out that it relates back to the value of n. Okay? If n is odd, if you have an odd value of n, how many petals? Well, for example, let's say we had if n was 3. How many petals would we have? 3. Then that's the same number of petals. If n is 5, you got 5 petals. N is 7, you got 7 petals. Okay? So if you have an odd value of n, that is the number of petals. If you have an even value of n, then it doubles. Then I'm going to put down you have 2n number of petals. Okay? Or however you want to write it on your sheet. Okay? So if n is 2, that means you've got 4 petals. If n is 4, that means you've got 8 petals. Okay? And so on and so forth. So those are the first two. Those should be pretty quick. Okay? What's the length of each petal and how many petals? You should be able to find those pretty quickly. Then we get to the location. And I'm going to kind of put 2 parts to create or figure out the location. One of them is, and I talked about this yesterday, how do you figure out the number of degrees between petals? And what do? How do we figure out the number of degrees between petals? Yeah, once you know how many petals you have, there's a whole lot of symmetry if you haven't figured that out yet. There's a lot of symmetry going on with all of these. And so you just take 360 degrees and divide it by the number of petals. That'll tell you the degrees between petals. Okay, so 360 divided by the number of petals. And I don't have room to write it down, so I'm going to just leave it here. That tells you the degrees between petals. Okay? That's how far apart they are. We're going to use that. Okay, that's going to be kind of the second thing we use to come up with a location. The first thing we're going to use is this. And we talked about this yesterday, and I'll show you an example. If you have a sine equation that you know is a rose, one of 2 things is going to happen when you graph this. Okay? Number 1, you're either going to have a petal on the 90, 270, the y-axis. Okay? And cosine would be the other one, by the way. You're going to have a petal on the x-axis. Or the other option with sine is you might not have any petals on any of the axes. They're just in the quadrants. Okay, and we'll talk about what to do in that case. But here's how we're going to figure that out. Here's what you're going to do. If you know that, if you're trying to locate, you really need to locate one petal. Because once you know where one petal is, then you can come right back to the number of degrees between the petals and just sketch everything else from there, off of that. So all you have to get started, in order to get started on a rose, you just need one petal. And then sketch from there. Okay, like I said, I'll show you when we get there. So when we get down to here, here's what I'm talking about. Since this is a sine, you would take your equation, you plug in 90 degrees for theta, or pi over 2 if you have it in radians, whatever. You plug it in and you see, what do you get for a value? Okay, if you get, let's say 2 or 4 or 5 or whatever, if you get a number other than 0, then you know that there's a petal of that length on that axis. Okay. If you get an answer of 0, that means there's no petal there. Okay, so if you plug in 90 degrees and you get an R value of 0, one thing you should have discovered too, by the way, all the petals come back to the origin. Okay, so if you get, that's why I say if you get an R value of 0, you're just finding the origin all over again. So there's no petal there. Okay, then you would plug in 270 if you didn't find anything on the 90 and see if there's anything there. If you get any value other than 0, then you know you found a petal. You found your first petal. Okay, and then let's say there was a petal on the axis. And let's say that there was 4 petals, which means they would be how far apart, by the way? 90 degrees. You'd say, all right, here's your first petal, and then 90 degrees later, here's the next one, 90 degrees later, 90 degrees later. That's how you can use the angles. You don't have to keep finding other petals by plugging in points. All you need is one to get started. Okay? Now, let's say for some reason you didn't find anything. Let's say you found no petals on the axes. In that case, then, what I want you to do, let's say there were 8 petals total. I'm just going to make up a number. Let's say that you found a rose, you know there's 8 petals, and none of them are on the axes. How many are in each quadrant then? 2. Sketch it. Sketch the approximate length and the approximately, I'm not going to worry as much on that scenario, exactly about like degree measures and all that kind of stuff. Sketch 2 petals here, sketch 2 petals in quadrant 2, quadrant 3, quadrant 4, with the approximate length that it should be. Okay? The only difference when you're doing cosine is now you're on the x-axis instead of the y-axis. You're going to plug in 0 degrees, And by the way, I think when you do cosine, it's always going to be on one of the axes. You'll find a pedal on one of the x-axis somewhere. Okay? Cosine, you don't end up in the quadrants, but only the quadrants. You will always find a pedal on an axis. Okay? So same thing. Plug in some values to get started, and then use the degrees to go from there. Okay? Does that make more sense? Does that clear some things up, hopefully? Okay, let's go to the last one. The limacons. Okay, limacons. So again, we talked about this process. Here's basically what you need. You need to know, to begin with, just based on the equation, which limacon are you dealing with. Then again, location. Just like I talked about with circles, are we on the positive x, the positive y, the negative x, the negative y? Where is the limacon located? And it could be any one of the four. You could have a cardioid that's on the positive x, positive y, negative x, negative y. Could be any one of those four locations. Same thing with a convex, same thing with the inner loop. It could be on any of those. And it's based off of the same thing that we'll get to here. And then the other part is you need the x and the y intercepts to at least sketch in. You need some points to kind of guide you a little bit. Okay, we'll talk about that. So let's start with which limacon. So I told you the other day, take a look at the ratio of A to B. Okay, and that'll help you. If you take A and you divide it by B and you come up with a number, you should be able to start to figure out what's going on. If, we'll see how much room I have here. If A over B equals 1, okay, meaning A and B are the same number, what do you have? That is a cardioid. Yep. That's how you recognize that you have a cardioid. If the ratio, when they're the same number, when A and B are the same number, you have a cardioid. Okay? When that ratio is 1. If that ratio is less than 1, what do you get? Anybody tell me? When the ratio is less than 1, what is it? That is an interlooped limacon. That's where you got the loop. Okay? This one is interlooped. Quick heads up, too, by the way, about the interlooped limacons. They will always cross the loop. As they create the loop, will always cross at the origin. No matter where the location is, when that loop comes and starts, it will cross. It always crosses at the origin. The loop does. Okay, just as a heads up. What if that ratio of A to B is greater than 1, but less than 2? That is the dimpled limacon. Okay? If your ratio of A to B is between 1 and 2, you have a dimpled limacon. Okay? And the last one, which I ran out of room, so I'm not going to write it down. If that ratio of A to B is greater than or equal to 2, then it's convex. If your A to B ratio is greater than or equal to 2, it is a convex limacon. All right, with me so far? Here's the first thing you need to be able to do on these problems. Take a look at your A's and B's and figure out what am I dealing with here? Which kind of limacon do I have? Okay, once you've figured that out, and like I said, there is a fourth one, I just didn't write it down because I ran out of room. Okay? When A over B is greater than or equal to 2, it is convex. Location, just like we dealt with on the circles. If your equation is a sine equation, that means you're going to be on the y-axis. It's either going to be above or below. It's going to be on the 90 or the 270. Okay? And again, anybody tell me? How do you know whether it's on the 90 or the 270? B. If B is positive, it's above. If B is negative, it's below. Okay? Just a reflection is all that is. But you're only focused on the sign of B. Okay? It doesn't really have, if A is negative, it doesn't have much of an, it doesn't change the graph much at all. Okay? On the other part, when you're doing cosine, you're on the x-axis, so you're either on the 0 or the 180 side. And same thing again. If B is positive, then you're on the positive side of the x-axis. Is b is negative, then you're on the negative side of the x-axis. You're on the 180 side. It's a reflection. Okay? So sine versus cosine tells you which axis. The sine of b tells you whether you're above or below, left versus right. Okay? So there's the first two. You figure out what you have, you figure out where it's located, and now the rest of this then is finding those x and those y intercepts. Oh, one other thing I forgot to mention as well. On the cardioid, I forgot to mention this as well. The cardioid, the point, always comes back to the origin as well. Okay? Anytime you graph a cardioid, just like I said, the inner looped crosses at the origin, the cardioid comes to a point always at the origin. Okay? So you always know that's one of the points on the graph. All right, x and y intercepts. How do I find the points then that are going to help me sketch this? So we're going to start with the same exact idea. Okay? We're going to start with r and theta again. If you know you're on the y-axis, if it's a sine equation, plug in 90 and 270 and figure out, all right, above, how far above the x-axis are we? How far below are we? Okay? Kind of the same idea. We'll plug some values in. If you're on the x-axis, same thing. Plug in 0 and 180. Okay? Now, there are some ways that you can use a and b to figure out kind of the length, where you're adding a or b or subtracting a or b. I'm not going to do it that way, only because it gets kind of confusing of, well, what if a is negative? What if b is negative? What if they're both negative? Then what? And it gets kind of confusing. This, to me, is a lot more straightforward. Okay? Which is why I'm doing it this way. And I'll show you it in an example so you can see what I'm talking about. But this will help you find kind of the first 2 points. So here, if you know you're on the y-axis, this would give you, I'm going to just make something up. This would give you, let's say, some point up here and let's say some point down there. Then we need to find the other intercepts. Anybody tell me the fastest way to find the other intercepts? There's a really fast way on this one. It's A. Whatever A is, will give you the other intercepts. Okay? Regardless. So on this one, I would have, I've got the ones, I've kind of got the, if you want to think of it as like the length of whatever the limacon is, the other intercepts would kind of give you the width. Okay? Or at least the other intercepts. And again, you'll see that when we do an example. Okay? But that's what A will tell you. It gives you the other intercepts that you didn't find from doing r and theta. All right, let me quickly hand out a sheet and let's go through a couple of examples so you can see this at practice, and then I'm going to give you a chance to practice it. Sheet from yesterday. This row, how many people needed in this row? How about this row? How many people need this sheet?
No, I don't need that.
Easton, did you get one or you need one? How many people in this row need one? Ellie, did you get one of these sheets yesterday? No, the actual like equations. So, guys in the back, did you guys get one already? Okay. Want to pass it back? How about this row? That? You guys need one? You guys have it. Trent, you already did. You guys are good. Okay. So take a look. Let's start with problem number 1. We're going to do 3 examples. We'll do 3 of these together. We'll do 1 of each type. That way you can kind of see the process on each one. And then I'll give you a chance to try it on your own. So let's take a look at problem number 1 here first. Very first thing, and what I'm going to do today, right now, I'm going to model what I'm going to be looking for when you take the test on Monday. Okay? So this is what I want to see this is what I'm going to look for when I'm grading the test. Okay? Number 1, what shape is it? It's a circle. There's point number 1 right there. Okay? Can you tell me what it is just based off of that? So I'm going to put down, this is a circle. Okay? Which means, what information do I need to know in order to graph a circle? 2 main things. Okay? And even more specific, I need to know where the center is and the radius. If you know where the center and radius are, you can always draw a circle. Okay? So let's start with that. Let's start with the radius because that's always easier. What's the radius? Yeah, it's your a value divided by 2, which in this problem is 2. We got a radius of 2. And then we also need to find the center point. Okay, where's the center of the circle located? Now, we know it's also 2, but the question is it 2 on the positive x? Is it 2 on the positive y? Which direction, which location? Where is the 2? Based on the equation, which one is it? Because positive x. The 4 is positive and cosine is x. So that tells you you're on the positive side of the x-axis, which means the center is the point 2, 0. So if we come over here and I put, there's the center of my circle. And now we use the radius just to find other points. We go 2 in each direction. Okay? So let's say I go 2 more. There's another point on the circle. Let's say I go 2 to the left. There's a point on the circle. Let's say we go 2 up. There's a point. And 2 down. And there is your circle. That's it. Okay? That's all there is to circles. Radius, center, and location. The only thing that'll ever change is the number of A. That 4 will be something else. Otherwise, and it might be sine versus cosine, but all that does is change the location. Okay? Make some sense, hopefully? So circles should be pretty quick. Okay? Let's do number 2. First question on number 2. It's a limacon. More specifically, which one? Why dimpled, Parker? And why? What reason did you come up with? Yep. If you look at your ratio, here's how you tell.
1 and 2.
So A divided by B.
Come on, stay focused here for a second. If you take a look at your A and your B values, A divided by B, 6 divided by 5, is 1.2, which is between 1 and 2, which means it's dimpled. Okay? So this is a dimpled limacon. Okay? So there's the first part. I know what it is. Now, just like a circle, where's the location of this dimpled limacon? Which axis are we on? Positive or negative x? For the exact same reason as what we had over here. If that 6 wasn't there, it's the same thing. Positive 5 and cosine means x. Your dimpled limacon's on the positive x side. Okay? That's where your graph is mostly going to be located, and therefore facing kind of to the left. You'll see what I mean by facing in a second. Okay? So you know what it is, you know where it is. Now we got to find the actual points. So let's do the whole r theta thing. Let's start with that. Because it's on the x-axis, I'm going to start with theta being 0 degrees. Here's why I had you take out your unit circle just in case you need it, and why you'll have it available to you on the test. If I plug in 0 degrees into that equation, what's the cosine of 0? 1. Times the 5 that's in front is 5, plus the 6 gives you 11. You just found your first point on your limacon. In the 0 degree direction, you're coming all the way out here 11. You can approximate it. I'm just going to say, here's 11 right here. There's your first point. Now, staying on the x-axis, let's go to 180 degrees. When you plug 180 degrees in, what's the cosine of 180? Negative 1. Times the 5 is negative 5. Plus the 6 gives you 1. Now, quick heads up. And I actually made this mistake in the other class, and then I fixed it at the end. As you go through and you take a look at this one, it's not 1 on the xy axis. This is an xy axis. It's 1 in the 180 degree direction. Okay? So we're actually 1 over here. Remember radius of 1, if you think about polar, if there were actual circles here, you're going 1 in that 180 degree direction. Okay? So there's your first 2 points. That's kind of the length of the dimpled limacon. And then we said to find the other intercepts, the y-intercepts in this case, where are they? Yeah, up 6 and down 6.
Wait, how do you, are they always A?
Yeah, always. The other intercepts that you're not finding versus r and theta are always A. Okay? Whether they're x or y intercepts depends on the equation. But in this case then, so I'm going to come up here to 6 and down here to negative 6. And there's some more points. And now we sketch in, to the best of our ability, the dimpled limacon. Okay? You'll see why I say to the best of our ability. Some people will be better than this than others. I'd be on the not so good side.
This looks like a heart.
So, should be something like that-ish. Okay. As long as I can tell what it is. Here's what I'm looking at. Told you I'm not on the good. I'm on the not so good side of this. Okay.
Oh, mine's too pointy. That's why.
Here's what I'm looking for, by the way. So if I were going to grade this, mainly what I'm looking for are the coordinates on the x and the y axes. And if you tell me it's dimpled, make sure that this is a smooth curve then, not a point. That's the only difference between dimpled versus cardioid, is if that's a point versus a curve. Convex would be you'd have like a straight line here, okay? That's kind of the difference between those three. Convex is straight, there's a kind of a smooth curve to dimpled, and it comes to a point for cardioids. Okay? Make sense? Doing okay? All right, last one. Go to number 5. Which, because of the way that I already taught this, you already know what this is, because it's the only one left. But you should be able to tell also based on the equation. Number 5. This is a rose. Which means, when we do roses, we need 3 things. Length of the petal, number of petals, and then location of petals. So let's start with length of petal. What's the length of the petal? Yep. Length of each petal that you're going to graph should have a length of 5 units. Number of petals. Okay. Remember, anytime you have an odd value of n, that's the same number of petals. Okay, so we are going to have 3 petals. By the way, what if that was a 4? Then we'd have 8 petals. Okay, yep, then we'd have 8. And then now we go location of petals, which remember were 2 things. We have to find the first petal and then use the number of degrees. Let's do the degrees first just because it's quicker. How many degrees apart are we? How many degrees apart are those 3 petals?
120.
Nope. Why 120, Parker?
3 divided by, or 360 divided by.
Yeah.
I just don't know how to do that.
360 all the way around, and you got 3 petals. Okay? So every 120 degrees, you've got a petal.
LOL.
Just using symmetry. Okay? So 120 degrees, I'm going to say 120 degrees apart. Okay? Or however you want to say that. Okay? Petals are 120 degrees apart. All right, so now the last part is I need to find a starting petal. I need to get my first petal. Since this is a sine equation, we're going to look on the y-axis then to see if I can find something. Okay? So if we do that, again, let's kind of go with the r theta idea. Let's take a look at 90 degrees. And you may or may not need the 270, okay? Because as long as you find one petal, then you don't have to find another one. You wouldn't have to do the 270 if you find it with the 90. If you don't find it with the 90, then you should try the 270, okay? So let's say I plug in 90 into this equation. 3 times 90 is 270. What's the sine of 270? What is it? -1. Which means then when we multiply it by 5, what I get is -5 for that value of r. How do I graph a -5? We plugged in a value on the 90 degrees.
So it's the bottom.
You just go the opposite direction. It goes down here. Yep. Or here's 5, technically. I'm not even going to put the negative. We'll call it 5. The negative tells you that we went, even though we plugged something in on the 90 degrees, the negative tells me I went down instead of up. Which means, there's your first petal right there.
So we don't even need another one.
Nope, we don't need another one. As long as you find the first one, now I can go to the 120 degrees apart to get all the rest of them. Okay? So now, if we just start going 120 degrees, now we can kind of approximate. 120 degrees approximately from there, you'd have another petal. Ooh, that's not what I wanted. Let's try again. Should be somewhere in there. And then another one, something like that. And there's your graph. Okay. Yeah.
Go down that pedal.
Because of the negative 5. If that would have been 5, I would have gone up 5 on the 90 degrees.
Doesn't matter, 'cause I-
Negative is always the opposite direction. Okay, remember when you have an R value that's negative, it's not a negative length, it's the other way. So normally, hang on. So normally, if I picked 90 degrees and got 5, I would have gone 5 up. Because it was negative 5, I went 5 down. Opposite direction from 90 degrees. What's that?
Oh, is it always the opposite direction of wherever you're coming from?
It depends on the equation. If anytime it's negative, yes. Anytime you get an R value that's negative, it means you're going in the opposite direction of 90 degrees. 90 degrees is straight up, so I went straight down 5. That's what the negative does. Okay? Or you can think of it as like a reflection if you wanted to think of it that way. So here's at least an example of each one of those types of problems that, like I said, that you need to be able to do. What I would like you to do then, with the rest of the time, you've got about a little more than 10, 15 minutes, somewhere in there. Try the rest of these, using only your lab to try to sketch these, find the important things, see what you can come up with. I did not give you an answer key on this one or the other sheet I'm going to hand out. Anybody tell me why? Yeah, just plug it into your calculator, the equation, and see if you did it right. Okay, so don't use a calculator while you're graphing it, but when you're done, just plug it in and see if you did it right. You can kind of check your own work. Okay? I am also going to hand out, so I'm hoping that maybe in the next 10 minutes you might be able to do the other 5-ish fairly quickly. I'm going to give you another sheet to give you some more practice because, not, like I said, you need to be able to do these things fairly efficiently.